Okay, this is continuing our conversation about current and just adding one other new idea to it. This slide here is just kind of fun to think about and know. Electric current, or a crap ton of electrons running through your body, is really what kills you, and high voltage can cause that. Voltage from our last unit we know is potential difference, but we could also think about it as like the oomph, which I'm not yeah, sure. Behind current. And so a big voltage can cause electrons to move faster. So if your voltage is high, usually your current will be high too, but technically voltage is not what kills you, because there are things that could slow it down. So these are just some different currents that if put on in your body, you'll feel. So this would be like feeling a shock. You can start to feel pain as it increases, but look how small these are. Muscle spasms, loss of control, like seizures. But if you have a current of just 0.07 that passes through your heart for more than 1 second, that will kill you. Now, if we think about like how this could happen, and there's a problem in the problem set that looks at this, we have to know one more idea, and this other idea is resistance. Because if electrons are flowing through a wire, that's easier than flowing through my body with all my cells and water and molecules and all that stuff. So resistance is a measurement of how much a material will slow down charge. And that's really this big idea next. A lot of the jokes on the first slide were about this symbol, which is called an ohm. And I usually draw it like this and then go like that and this. And resistance is the letter R, and it's measured in ohms. Now, resistance is the amount that the conductor, could be like a wire, my body, whatever, resists charge. So resistance is going to slow down current. It's part of kind of the name of it in resist. It happens because electrons, like we see a wire here, and we're thinking, oh, electrons are just moving perfectly through the wire. But it's not quite like that. It's like a high traffic zone, like a freeway with a bunch of traffic. And also the electrons are bouncing around, and they don't just go straight. They're like, oh, and they kind of bounce around and move along, and that just slows them down. So in our labs, we are going to add resistance into circuits by using these little things called resistors. Resistors are these. They're just these very small little straight things, and we'll talk about how the colors mean things. But any electronic device resists current flowing through it. It slows it down. Light bulbs slow down current, motors, toasters, anything. As current has to flow or electrons have to flow, things are going to resist it. So current, resistance, and this idea of voltage, or the oomph behind current, come together in the number one equation of our unit, called Ohm's law. The math of it is really simple. The voltage, in units of V for volts, equals the current in units of A for amps, times the resistance. And that's it. This little picture is a bit dorky, but it really helps me think about, and helps my students think about what's going on. So this little sad guy is amps. That's current. And so current is trying its best to flow through. Volts, it's trying its best to push current through. These volts and amps are kind of working together. One goes up, the other goes up. Ohms, on the other hand, or resistance, is trying to slow our poor little current guy down. And so that's the relationship between these three things. So I'm going to do one example in your problem set and show you the simulation. And the simulation will really talk about this relationship as well. So number 3, I'm going to do 3 and 6. You do 4 and 5 on your own, and you can also find it on the key on the overview page. So a circuit has a single resistor and is attached to a 9-volt battery. If the current flowing through is 0.4 amps, remember current is I, not C, how much resistance is in the resistor? Well, V equals IR. V is 9, I is 0.4, and then R. Math-wise, all we have to do is divide. $22.5. And then our unit here is ohms. I'm going to switch into number 9 because it's kind of fun. If I grab a power line that has a voltage of 400,000 volts, which big power lines can have even more than that, with dry skin, what is the current running through my body? So V equals 400,000. The human body has an estimate of 500,000 ohms of resistance. Now, the dry skin is important because if you're wet with water, and then additionally, if it was like salt water for some reason, you're swimming in the ocean and grabbing power lines, it's really dangerous because the salt helps and the water help electrons move faster and reduce your resistance. But anyway, we're trying to survive here. We're going to see if that's possible. Will I die? And what is the current? So we want to find out current, and then we can use your notes to figure out if that current is above 0.07. That's really small, so we can already kind of guess. Yeah, sorry. That's why you don't go grabbing giant power lines. But let's actually find out what it is. So V equals IR. V is 400,000. I is what we're solving for. Resistance of the dry human body is 500,000. So we have to divide by all these gigantic zeros. .8. And 0.8 amps is way bigger than 0.07. So, yeah, please don't go grabbing power lines. So for the rest of class and for the rest of your time, you are looking at a simulation, link on the class log, answering these various questions about the relationship between voltage, resistance, and current. When you are done with the simulation, it's your work time on quest 1 through 4. If you are done with that also, then it's your time. We will go over with a bell work tomorrow some of these equations and the vocabulary if you guys have questions. Bye.